You know those super long, messy web addresses? Ever wonder how services like TinyURL or Bitly magically shrink them into just a few characters? Well, today, we're going to pull back the curtain and design one of those services ourselves, from scratch all the way up to a massive system that can handle billions of requests.
Okay, so here's our roadmap. First, we'll get into the why. Why do we even need this? Then, we'll wrap our heads around the incredible scale we're dealing with. After that, we'll tackle the main puzzle, how to generate those tiny little keys. From there, it's all about building. We'll blueprint the service, figure out how to make it handle insane amounts of traffic, and finally, put all the pieces together into the final architecture.
So, first things first. Before we can build anything, we have to know exactly what we're building. A URL shortener sounds simple on the surface, right? But getting the goals straight right at the beginning, that's absolutely critical. Let's nail down what this system really needs to do.
At its heart, this is what it's all about. We take a ridiculously long link, like this monster on the left, and we turn it into something short, sweet, and easy to share, like you see on the right. This is a game changer for social media, emails, and pretty much anywhere you don't want a giant wall of text.
Okay, so what does our service actually have to do? Well, it boils down to 4 main jobs. First, make a short link. Second, when someone clicks it, send them to the right place. And for some extra polish, we'll let users create their own custom links and even set an expiration date. These are the basic promises we're making. But here's what's just as important: how the system behaves behind the scenes. It has to be up and running 24/7. I mean, if our service goes down, every single short link out there just breaks. The redirects have to be lightning fast. We're talking milliseconds. And for security, you shouldn't be able to just guess someone else's short link. And now, let's talk about scale. This is where the real fun begins. We're not just building a handy little tool, we're designing a piece of core internet infrastructure. And the numbers we're about to look at are frankly staggering. Let's start with how many new links we're creating. We're aiming to handle about 500 million new URLs every month. If you do the math, that breaks down to our system needing to process around 200 new link requests every single second, nonstop.
But here's the kicker. This system is what we call read heavy. For every one person that creates a link, we expect about 100 people to click on it. That means our read traffic is 100 times bigger than our write traffic. We're talking about 20,000 redirection requests per second. That is a ton of traffic.
So where are we going to put all this information? If we plan to keep these links around for 5 years, we'll have about 30 billion records to store. Even with tiny records, that adds up fast. We're going to need at least 15 terabytes of storage. Just to put that in perspective, that's thousands of movies worth of data.
Okay, so we know the scale is massive. That brings us to the absolute core of our system, the central puzzle we have to solve. How on earth do we generate a unique, short, and random key for every single one of those billions of URLs?
Broadly, we've got too many ways to go. Approach 1 is to take the long URL, run it through a hashing function, which is kind of like creating a unique fingerprint, and just use the first few characters. The big risk there: collisions. 2 different URLs could, by pure chance, get the same fingerprint. The second, much safer approach is to just generate a massive list of unique keys ahead of time and keep them in a database, ready to be handed out.
And that offline approach is definitely the way we're going to go. We'll build a dedicated key generation service, or KGS. Its only job is to sit there and crank out billions of unique keys and stuff them into a database. Then, when our main service needs a key, it just asks the KGS, "Hey, give me one." It's simple, it's fast, and it completely avoids that whole collision mess.
Awesome! We've got our key generation strategy locked down. Now, we can start sketching out the actual blueprint of the service. And like any good building, we're going to start with the foundation, the database.
You know, what's really cool about this is how simple our data structure is. We basically just need 2 tables, one for our users and one that does the most important job, mapping the short key, the hash, to the original long URL. And since we're just storing billions of these simple key value pairs with no crazy relationships, a NoSQL database is the perfect tool for the job. It's built for exactly this kind of scale.
Okay, a database and a key generator are a good start, but they would absolutely melt under our traffic load. To handle 20,000 requests every second, we need to bring in some heavy-duty tools to make our system totally bulletproof.
First off, we can't rely on just one server. That's a single point of failure. We're going to have a whole army of them. And sitting right in front of them, we'll put a load balancer. Think of it like a traffic cop for the internet. making sure every request goes to a server that has capacity, spreading the work out so no single machine gets overloaded.
Remember those 20,000 reads per second? Hitting our main database that often would be a complete disaster. So we'll add a cache. This is like a super fast memory layer where we store the most popular, most frequently accessed URLs. If a request comes in for a hot link, we can just grab it from the cache in a flash without ever bothering the database.
And what about that 15 terabytes of data? No single database server can hold all that, so we'll spread it out using a technique called hash-based partitioning. We just take our short key, run it through a hash, and that result tells us exactly which database server holds that piece of data. This lets us add more and more database servers as we grow. It lets us scale horizontally pretty much forever.
So we've covered a lot of ground. We have our requirements, our key generator, our database choice, and our scaling strategy with load balancers, caching, and partitioning. It's time for the big reveal. Let's put all of these pieces together and see what our final system looks like.
So the big question is, how does this all work together? How does a single click on a TinyURL flow through this complex system of load balancers, caches, and distributed databases to get you to your destination in the blink of an eye?
And here it is, the whole shebang. A user's request comes in from the left and hits our main load balancer. That directs it to one of our many application servers. Now, if it's a read request, someone clicking a link, the server first checks our super fast cache. If the link's there, boom, we send them on their way. If not, we ask the database. Now, if it's a write request, someone creating a new link, the server asks our key generation service for a fresh key. Then it saves the new long and short pair into the correct database partition. It's like a perfectly choreographed dance, all designed for speed and reliability at a massive scale.
And there you have it. That's how you design a URL shortener that can handle a huge chunk of the internet's traffic. But this system, as robust as it is, leads to a new question I want to leave you with. What would you add next? Better analytics to track clicks? More advanced security features? Because, in the world of system design, a good design is never really finished. There's always room to improve.